All right. Next presentation, Team 48, Vehicle Power Delivery and Data Handling for an Electric Formula SAE vehicle.
We get to start?
Yes.
Hello everyone, my name is Colin Roberts. With me are Jason Knott, Jimmy Pham, and Matthew Yuja, and we are Project 48. So starting off with a little background, the Formula SAE competition challenges students to design, manufacture, and compete their own small Formula-style race cars. This year, Tiger Racing has made the transition from the internal combustion competition to the electric vehicle competition.
Since this is the first year that the Tiger Racing team is going to an EV car, we are dealing with the control systems and data handling of the vehicle. Some of the implementations that this project consists of are traction control, variable power modes, vehicle health display, and data handling. So some of the objectives of this project are to display information to the driver in real time. We also want to improve time in the acceleration event with traction control. We want to improve with the endurance and efficiency event also with variable power modes. And we want to transmit and receive data throughout the vehicle.
So moving on to our customers, obviously our primary customer is our sponsor, the LSU Formula SAE Tiger Racing team. But we also have a one-to-one transfer of usage to other Formula SAE and Formula student teams. Our secondary customers are consumer automotive companies who might want to utilize our technology to better improve their vehicles, as well as teams in other racing divisions that can use our racing technology for their purposes. Moving on to our existing and competing technologies, we are in direct competition with last year's Driver Controls Senior Capstone project, specifically with our wheel speed sensors. In our analysis, we found that these failed due to excessive vibrations due to their diving board design, which we intend to improve on, as I'll explain later in this presentation. Our next direct competitor is the 2122 Tiger Racing internal combustion car, specifically the vehicle health display. This is based in the AIM suite, and this sensor suite is designed for the AIM EVO 4 or 5 data logger. And this sensor suite works very well for IC, but not so much for EV, and I can answer some questions on that later if you have any questions there. And we're also competing with other FSAE teams as we want to give the team a great return on investment and help them win that competition. Moving on to our indirect competition, we're also competing with current consumer vehicle technology in the form of traction control and driving modes. And also professional racing teams have traction control technology as well as driving modes and vehicle health tracking in the form of live telemetry.
So here's the functional requirements at the top. We want to provide low voltage power because without this, we're not going to be able to have any of our implementations operate. So it's very impactful. We also want to display, receive, and transmit information. And under that is activate traction control, which will be done in a toggle switch. On the second page here, we have adapt motor speed requests, register power mode selection, and scale DC current. And these bottom two are going to be for the variable power modes. So for the qualitative constraints, the main two takeaways here are safety and FSAE rules. We want to make sure that everything we do is not putting the driver in harm's way, as well as anyone around the vehicle. And we want to make sure that our implementations don't violate any of the FSAE rules so that we can still compete. So for the quantitative constraints, these are all represented by numerical value. The big takeaways here are our implementations. We don't want to exceed 2.5 pounds. We want to have 3 dash display pages, and we want to have 5 variable power modes. And for this side, it's kind of a keynote that we're going to have for the dash and the wheel speed sensors, we're going to be operating off the 12-volt power supply. And for the dial and the switch, it's going to be operating off the 5-volt internal power supply and the VCU.
So we have the function tree for this project that includes the main 3 functions that we want to implement. First being the vehicle health display. We want this display to receive 12 volts from the low voltage battery in order for it to operate. We wanted to receive information in the form of Tiger Racing EV sensors such as coolant temperature, brake pressure, accelerator pedal position, as well as the Tiger Racing battery management system, the Tiger Racing motor controller, and the vehicle control unit. We then want this display to display this various information that receives to the driver in real time. For traction control, we wanted to receive power in the form of 12 volts for the wheel speed sensors, as well as 5 volts from the VCU's internal supply for the toggle switch. We want the system to receive information in the form of driver activation, as well as front and rear wheel speeds. We wanted to calculate the slip ratio, which will determine if the car is slipping while driving. And under slip, we want that we want the algorithm to reduce the pedal position automatically to stop this wheel slip, and want this pedal position to be transmitted to the motor controller, where it will control the motor and adapt the motor speed request. For the variable power modes, we want the selector dial to receive 5 volts from the VCU's internal supply. We want the VCU to receive this input voltage and convert it to a DC current scaling factor. And we want that scaling factor to reduce the max DC current set point, which is then sent to the motor controller, which will limit the max DC current draw from the high voltage battery.
So moving on to our concept generation, evaluation, and selection. Starting off with the dash display, we looked at 5 options, but narrowed these down to 2 specific options: the Plex STM 330 DLG and the AMGS dash that has been used for multiple years now. So looking at our scales, the cost and the weight are the highest. Given that we're a collegiate racing team, we want to keep costs low, but also keep our weight down to make sure that we're moving as quick as possible. So after performing this decision matrix, we found that the Plex STM 330 DLG was the best fit for our application.
And for the wheel speed sensor selection, we looked at various different sensors. If you look here in the bottom right, it shows the wheel speed sensor that the previous teams had used. We have decided to not go with this sensor due to its shape. And if you look at the one on the top here, this is the wheel speed sensor that we decided to go with. The main reason being that it's shaped and it has a fully threaded base, which will allow for a lot more mountability, and it'll be able to withstand a lot more hostile environments. And if you go to the next slide here, we'll be able to see how it is mounted.
So yeah, moving on to our mounting for the wheel speed sensor. As stated before, it'll be threaded into the upright as shown in the red box. There are included lock nuts sent with the sensor to keep it secure in the hole. And the threaded nature is twofold. One, it lets you attach it in and screw it in to reduce vibrations, but it also lets you it allows for adjustment of the sensor distance from the gear tooth ring. And that allows for us to fine tune the accuracy of our sensors in the spring when we're testing.
So for the traction control system, the product architecture, the system is activated using a toggle switch in the cockpit. The system will be activated and the front and rear wheel speed will be measured using a gear tooth ring and Hall effect sensor, as you've seen previously. These speeds will be sent to the VCU, where they are prepared to detect wheel slip. And when that wheel slip is detected, we want to reduce the motor speed request based on this difference in speed.
Yes, so for variable power modes, the driver will select a position on this dial, and that will be one of the power modes, and that will depend on the event, which position they are in. This dial will send a voltage to the VCU, and this VCU will then convert that voltage to a current scaling factor, and then that new current will be sent to the motor.
So moving on to our vehicle health display, it starts with the Tiger Racing sensors and fault detectors, which are in the appendix. This information is sent to the vehicle control unit, and that processes the sensor data and monitors faults. And these faults and sensor data are presented on the display, which will be discussed a little bit later. And our dash display will be attached to the dashboard using the included mounting hardware.
So if you look at the vehicle health display, right here we got some LEDs, and right here we also have some LEDs. So on the left and right, there's 2 each. So these 4 LEDs are gonna represent if the vehicle has a fault, and the 8 LEDs on the top are gonna represent the battery life. So now for the screen, this is gonna be the main screen to see, the driver's gonna be able to see when the car is being driven. We have a lot of sensor information from the Tiger Racing sensors as well as the wheel speed sensors that we're implementing. And we're also gonna have 2 more pages that are just also gonna be some Tiger Racing sensors along with the wheel speed sensors. And these are more for testing instead of driving. And on the 3rd page, this is the final page here. And we're gonna have fault and warn description at each page, just in case the driver forgets what the LED is indicating. And all these pages are customizable in case we get any new information from our sponsor.
So the VCU, motor controller, battery management system, and dash display will communicate using this CAN bus. This CAN bus calls for a shielded twisted pair with 120 ohm resistors on each end of the bus. And all the components send information in the form of this CAN message, with emphasis on this 11-bit identifier, which will be mapped to a particular message. So So here's the CAN bus diagram for this project. As you can see, we have the VCU and BMS on both ends, and we have the digital display and motor controller spliced into the main wire. This is because the VCU and BMS are both manufactured with internal 120 ohm resistors and shield terminations. So here's the Simulink model for our traction control system. The inputs to this model are the toggle switch output voltage from the driver and cockpit, as well as the front and rear wheel speed frequencies from the gear tooth ring, as well as the tag racing accelerator pedal position voltage. And what we want to receive from this subsystem is the new pedal position that will be sent to the motor controller in order to adjust the speed. So for the driver input, we are going to be using this toggle switch connected to a digital input on the VCU. As you can see, when the toggle switch is closed, it will allow current to flow to ground, and the VCU will see 0 volts. And when the circuit is broken or the toggle switch is turned off, no current will flow to ground, and the VCU will see its own internal 5 volts. So here you have some data from the 2019 Tiger Racing Endurance. This was actually the last time that they were able to implement the wheel speed sensors correctly, so this is the last year that we have this data. From the graph, you can see the green line is the front wheel speed, and the rear is the green is the front wheel speed, and the red is the rear wheel speed, as this car is a rear wheel drive. And the dotted line is the rear wheel speed limit set by the slip ratio in the Simulink model. And that can be adjusted to be more or less forgiving depending on what the team requires. As you can see, at around 5 seconds, the red rear wheel speed exceeds the green greatly, and this indicates a high, an event of high wheel spin. So when the traction control system is turned off, this wheel spin will be allowed to happen. But if we turn the toggle switch on, the system will be activated, and if the system detects that the rear wheel speed is above this dotted line, it will then reduce the speed to keep it within the this dotted line here, and that will mean that we are in an allowable slip range.
So these are the variable power mode names and their corresponding currents. These were calculated using the event times and the battery capacity of 16.2 amp hours. For the acceleration event, it will get full current to the motor because we want the fastest possible straight line speed, and this event will last about 17 seconds. The autocross event will happen right after the acceleration event on the same charge and will last for 10 minutes and 17 seconds. And for the battery to last that amount, the current or the motor will draw a current of 79.78 amps. The endurance event will happen on a separate day on a full charge, and the sponsor has given a target time of 30 minutes for that event, and so for the battery to last those 30 minutes, the motor will draw 29.16 amps. And to account for driver error and over driving the car, a 10% reduction of the endurance current will be implemented, called an eco mode, which will yield 26.24 amps, and a lit mode will be implemented, which is 10% of the max current, so 18 amps. The selected dial for the variable power modes was measured for resistance at each of its 5 positions, and they are found here in this table. And a 2K ohm pull-up resistance will be implemented. And to find the output voltage of the selector dial, the circuit was simulated with a 5 volt supply from the VCU to the 2K ohm pull-up resistor, and the variable power mode dial is shown here with its resistance change as corresponding to the found values. And here are the output voltages that were found in the simulation.
So here's the Simulink model for variable power modes. We got here on the very left is the rotary position, which will be determined by the driver. And since each position has a different resistance, this is going to give a different output and voltage as well. This voltage is then going to go to a lookout table where the scaling factor is determined. And that will give you the DC current that is coming from the motor. So here's a better representation with the position, scaling factor, and max current all alongside each other. As you can see, the scaling factor is going to determine the current, and that is ultimately determined by the position. And on the graph here, it shows a simulation of the driver switching through each different dial position in a 10-second time period.
So moving on to the wheel speed sensor mounting, I started off by looking at what our allowable major diameter in the threaded region was for those for the threads that are on the sensor, and I was given a allowable range of 10.94 millimeters to 11.91 millimeters. And our original major diameter of this threaded region was 11.57 after adding this implementation. Moving on to the next page. When I'm writing the FEA, I have those boundary conditions in the appendices if you have any questions on that. But I found that the deformation in this threaded region was 0.121 millimeters, resulting in a major diameter after deformation of 11.45 millimeters, which did fall in our range, and this solution did converge. Moving on to our factor of safety FEA, our goal was to have a factor of safety of over 1 just to make sure that it's not failing, but our ideal scenario would be around 2 to 3, to give us some wiggle room in case any assumptions or any unforeseen circumstances occur. And we found that the lowest factor of safety in this mounting region was 3.3, and this solution also did converge, and it used the same boundary conditions that are found in the appendices. Moving on to our vibrational analysis, as I mentioned earlier, last year's wheel speed sensors failed due to excessive vibrations due to their diving board design. So for this exercise, I'm assuming that there are no vibrational losses between the rotor and the sensor to give us a worst case vibrational scenario. And I'm also assuming that in the event of a crash, your sensor accuracy has negligible importance. And that lets me max out where our max shock is that the sensor is experiencing, as if it's crashed, we don't need that wheel speed measurement anymore. So according to our technical sheet, we found that they specified that their allowable vibration is sinusoidal, and it's 15 G max from 40 hertz to 2 kilohertz. We also were told by that technical sheet that our mechanical shock resistance is 50 Gs. So looking at the bottom left table, or the bottom left figure rather, it shows that they are experiencing 17 hertz at around 60 miles per hour, which is what the max speed I've seen in our driving data. So in my research, I also found that the road-induced vibrations tend to be between 10 to 22 hertz, which is below our vibrational range. And according to the 2023 FSAE rulebook, a crash is considered to be any scenario where 8 to 11 Gs are occurring, and that is below both our shock resistance and our 15 G max value.
So here we have the gear tooth dimensions. I calculated these dimensions keeping in mind I wanted to save as much material as possible while also having the highest wheel speed sensor accuracy and resolution. So as you can see the tooth amount for each, the front and rear is different. This is because the hub on the rear, the radius from the middle of the hub to the sensor is larger, so we're able to fit 2 more teeth while keeping in these minimum requirements from the wheel speed sensor data sheet.
So moving on to our gear tooth deformation, I selected a material of AISI 1020 cold rolled steel, which I will discuss on the next slide. In terms of boundary conditions, I fixed it to have, unfortunately, this picture does not have our axes, but the Y direction is the vertical axis. So this is constraining it from moving vertically and allowing it to expand or deform outwards. And I also applied an external load of centrifugal load, of 1625 RPM. That is the MRAX motor 6500 RPM scaled down using a 4-to-1 gear reduction that is on the car currently. And I found that this region with the tooths deformed by 0.002 millimeters, which was very low, and told us that we'd still be in an accurate range, and this solution did converge. Moving on to our material selection, we had 2 material constraints coming from the wheel speed sensors. First, the material had to be ferrous due to the use of a Hall effect sensor, which utilizes magnetic fields. And we also were told by the technical sheet to use a cold rolled low carbon steel. So we selected AISI 1020 cold rolled steel for two reasons. One, this is a material that's already used by the team in many applications, and every year they have waste that just sits in the shop. So we identified this as a good candidate to be used. And we also confirmed with the wheel speed sensor manufacturer that yes, this material will work well in this application.
Here's our electrical component selection. As you can see here, we have the dash to start it off with. And as we look into our budget in the future, we'll see that the dash is not included, but it is a very corresponding effort between Tiger Racing and our project to determine what the dash will be. To the right of that, we have the wheel speed sensor, the toggle switch, the rotary dial, and some wiring that we'll be using throughout this project.
Moving on to our manufacturing plan for the mechanical side. For the wheel speed sensor mounting, this is integrated directly into the Tiger Racing uprights, and the team sends this upright out to the AMMF each year to be machined. We're also purchasing, as you'll see later in the budget, a 1536 to 32 tap, which will be used to create threads by hand in the mounting hole. Unfortunately, the shop did not have one in their inventory. Moving on to the gear tooth wheel, this will be machined by Tiger Racing sponsor Custom Metalworks. So the team provides their own stock, and Custom Metalworks machines it for free and sends it back. And then lastly, for the dash display mounting, we're attaching the dash display to the dashboard of the vehicle using the included mounting hardware.
So as far as the electrical side, the CAN bus, as well as the traction control algorithm and the variable power modes code launcher will be implemented, and the BMS and motor controller will be configured to interface with the VCU. As far as wiring goes, the sensors will use 22 AWG wire gauge for powering, and the CAN bus will use the same gauge, but will be shielded and twisted paired. Connections, the VCU has pins, so female-to-female connections will be used. Wheel speed sensors will be connected to the VCU by its own internal wires to a 22 AWG wiring gauge extension to a female-to-female pin connector to the VCU.
So moving on to our spring testing and validation plan. Starting with our testing, we're wanting to show that our technology is functioning correctly as a baseline. Starting off, we're planning to perform a CAN bus and analog communication test. That way we can assure that our sensors and all components are communicating correctly, and this will help us to test the functionality of our data handling system. Moving on to the variable power modes, we want to run a variable power mode DC current test to establish that that technology is functioning correctly. And lastly, we want to move on into a wheel speed sensor frequency test to test that the traction control technology is working correctly. Moving on to the validation phase, this is where we're proving that our implementations are fitting our objectives and constraints. So starting off, we want to start with the dash display driver surveys, which is a non-technical test, but given that this is also an ergonomic type system, it's very important to make sure that the drivers are happy with what they're seeing. And this also opens the door to implementations such as a specific setting for each driver, letting them tailor what they want to see on each page, which will let them be able to glance down quickly while driving and know exactly where to look for their information. Moving on to our traction control validation, we plan to run both bench and driving tests of the wheel speed sensors, the bench test being on a motor in a shop with a known speed, and determining that our wheel speed sensors are reading the same speed that motor is running at. And that's a extension of the wheel speed sensor frequency test. And then after that, we'll be running driving tests, during our practice sessions to make sure that the traction control technology is helping the drivers rather than hampering them. And lastly, we'll be running mock endurance runs as well as potentially autocross and acceleration practice runs. And that'll be used to test our variable power modes technology and making sure that not only do we have ample battery life remaining, but also seeing if we can give a little bit more power to give that much more speed in the events. So moving on to our safety considerations, it all starts with the rule book. If you can't pass the rule book, you don't compete. So this document lays out all of your safety considerations and any other considerations that are needed to be taken into account in your vehicle design. Moving on, we also will be working in the FSAE and the AMMF workshop, so we need to make sure we're safe in there. And that all starts with wearing proper PPE while inside the shop. This includes closed-toed shoes, long pants, safety glasses, and fitted shirts. We also want to make sure that nothing's loose, such as jewelry or hair, and we also don't want to wear any gloves while working with heavy machinery, as those can get stuck in the machine. And we also want to make sure that we don't operate machinery while tired or distracted. As college students, everybody knows that we're grinding on projects very late at night, and that's when mistakes tend to happen. So you want to make sure you're not working with machinery, as a mistake can be very costly. Moving on to high voltage safety practices, given that the car has a very high voltage running through it, you want to make sure that you're safe around that type of voltage. So first off, you want to make sure that you're using one hand whenever possible to avoid completing the circuit. You also want to be mindful of metallic objects and fluids when you have live equipment to make sure that you aren't, putting yourself in danger. You also want to make sure that you're avoiding connecting the circuit to the last step to make sure that everybody is clear, all safety procedures have been met, and that you aren't putting anybody at risk. You also want to use proper PPE, such as high voltage rated gloves and insulated tools, and you don't want to touch the car if the tractive system voltage has not been measured, or if the tractive system active light is red, signifying that there is high voltage running through the vehicle.
So for environmental impact, manufacturing waste will come from metal shavings, cutting fluid, oil, and electrical energy coming from machine use, and plastic waste will come from packaging. Operational waste will come from power generation for the low voltage battery, as well as replacement for components. And end of life waste will come from disposal of all electrical components, and certain materials will be recycled. For the project budget, the team was given a budget of $750, and most of that budget went into the purchasing of low speed sensors, with for them totaling to $151.80. And after all components are purchased, the team will have a remaining budget of $375.25. For the fall project timeline, starting off, the team established an overall project scope and established overall functions and constraints. And moving on to the ideation phase, the team established component constraints and finished off that phase with finalizing component selection. For the design and analysis phase, the team designed the physical aspects of the project scope as well as the code logic, and ran FEAs for the physical aspects of the designs. And ended off the semester with finalizing manufacturing and implementation plans for the spring. Moving on to the spring timeline, the team will start by manufacturing the physical designs that were designed from the fall semester, and as well as route wires to components and interface components with each other. For validation, the team will bench test low speed sensors and test CAN bus communications, and end off the semester by tweaking the display pages based on driver feedback and testing low speed sensors under driving conditions.
This concludes our project, and we'll be happy to now take any questions that we have.